Thank you for having me here. I'm really excited to be here today to speak about streaming, which has been the theme of research for the last years. So in the new world, it will not be the big fish, which eats the small fish, but the fast fish, which eats the slow fish. This is what Klaus Schwab said this year at Davos. And he's the founder of the World Economic Forum. And the reason for this is that change brought about by technology, by advancement in technology, is accelerating and continuously modifying the business landscape. So agility, nimbleness, and speed are becoming fundamental characteristics for survival, not just size. Streaming analytics and online analytics can enable a company to drive faster insights, and this will this will enable a company to derive faster insights, and these faster insights will enable survival because they are a key ingredient for agility. After all, you cannot really avoid a blow when you see it too late. So this is the reason why we need to shift the focus from just big data to fast data. So that you might consider how streaming analytics fits in your general data strategy. Today, I will be answering 5 questions that have been asked over the years multiple times, and that you might be asking yourself too. First, I will define what we are speaking about, what is online analytics. Then I will speak about why you should care about it. And once I convince you that it's worth, how you do it. And finally, I will explain where does it apply and when you should start caring about it. So consider this the outline for the next 30 minutes or so. So, by the way, if you have any questions, feel free to interrupt me. So what is that we're speaking about? What is this streaming analytics? Let's start with what we're analyzing, a data stream. A data stream is just a sequence of data items read one after each other. So a file, if you read it sequentially, is a data stream. How is it different from what we are used to already? So most of the research in innovation in recent years has been devoted to this problem, to the big data problem, when you have a lot of data and they are too big to handle. And the amount of data that we deal with today is astonishing. Typically, this data is accumulated over a large period of time. For example, at Yahoo, we used to deal with several months of query logs at a time, so looking at what people search on the search engine. And so this data is very large, but today, not only we are dealing with large amounts of data, but we are producing data faster and faster. So we are producing what we call big data streams. The data itself, we are not measuring it anymore in bytes or gigabytes, but we are measuring it in time. So we produce gigabytes per hour, terabytes per day. And we need to continuously deal with this flux of data that is coming inside the companies. So it's not just about dealing with the data once and for all. You have to deal with it continuously. And of course, this is a challenge. However, this data is also an opportunity because you have enough data in a short period of time that by analyzing it, you can make informed decisions. So this is also the opportunity that big data streams provide. So we want to analyze this data. We want to do stream analytics. And this means having a model for your data. Because data without a model is just noise. And the model can be as simple aggregations or segmentations of your data. or as complicated as statistical machine learning models. In any case, it's a model. And what you want to do is to fit your data to the model, which can be just aggregating, as I said, as counting, or doing fitting of a statistical model. So in a streaming environment, you can do the same thing that you would do with a batch environment. Because in the end, consider that data is almost never produced as a batch. It's always produced throughout time. So you have people that clicks on websites day or do calls, and then you have call logs and so on and so forth. So actually data originally is a stream. And then often we batch it together for ease of analysis. So whatever we are used to do with batch analytics, we can do with streams. And usually people divide these things in three main components. There is descriptive analytics, which means understanding what is happening now. There is predictive analytics, which means understanding what is going to happen in the future, and prescriptive, which means automatically dealing with what is going to happen in the future. And we are usually very good with the descriptive, reasonably good with predictive, and prescriptive is still a bit out of reach, but that's the target in the long run. The difference between doing batch analytics and doing stream analytics lies in where the value of data is. If you have batch analytics, the value of data lies in the aggregation. So you have a large amount of data, then statistical patterns and trends start to emerge when you slice it and dice it in the right way. The value in a stream instead lies in the freshness of the data. I know that something just happened. That's what a stream tells you. So let me give you an example from web technologies, because that's my background. We have queries, right? So at Yahoo, we had years and years of query logs, and we know that, for example, people would search for boots in winter and would search for Bahamas resorts in summer. So this is something you can see by aggregating a lot of data from different people and throughout time. And this is good and nice. You can explore this with Google Trends, for example. However, if I tell you that I just looked for Bahamas, this is different because you can act upon it. So if I just looked for Bahamas on the search engine, you can show an advertisement for some Bahamas resort, right? So that's the difference between the value in aggregation and the value in freshness. And this is actually how Yahoo, Google, and all these people make money. Now, what we want to do then is to leverage this freshness. And the way to do it is with online analytics. I want to make a point that online and real time is slightly different, so there is some confusion sometimes with the terms. What I mean with online is that we would rather analyze the data as it comes without storing, rather than storing it and analyzing it later, okay? So that's what I mean, online or streaming analytics. Real time has a stronger meaning. Real time means that I have to answer within a bounded amount of time. For example, if I'm designing the brakes of your car, they need to answer within 0.1 milliseconds from when you press the pedal. Otherwise, it's a problem. And this is not usually a problem in our setting, because if you have your answer within 1 second or 5 seconds, it's usually not that big of a difference. Okay, so now I have probably explained you what we're speaking about. Now I would like to tell you why you should care about it. And let me ask you a question. How many people in the audience read all your emails in bulk once per day? Raise your hands. Only once per day. That's very good. Yeah, most people don't. I don't. There are many people that advise to do this because it's very efficient. However, because context switching basically is very expensive for human beings. However, this is not the most effective way to deal with it, because probably there are maybe people that are waiting for your answer. So we don't do that. We answer usually as fast as possible, and we answer asynchronously. And the same thing is true for business and data processing. However, we have a legacy from the time when computing was expensive. So batching things all together was a way to make it more efficient. And we still reason and process data the same way. However, what usually happens in a company is, quoting Jay Krebs, who's the founder of Confluent and a former LinkedIn employee, is that something happens, some new information arrives into your company, and you want to respond to it asynchronously. That's what happens. And this fits very well with the streaming paradigm, with stream processing. However, very few things are done asynchronously yet. We are still doing everything in a batch way. What we need in order to create an asynchronous processing architecture is what I like to think of a data nervous system. And I will compare it with the data silos that are typical in today's business. So a data nervous system is something that digs into your processes and alerts you whenever something happens, and then allows you to answer asynchronously to the new information that arrives. Think about the nerves as the sensor. So you want to instrument your process in order to get a stream of data that tells you what's happening. And then you have the central nervous system, which is the backbone that collects all these signals in a single place and drives them to the brain, which is where you make sense of all these signals. So it's the analytical power of your data nervous system. And the good thing about this is that if you want to build a new analytical application, which means to make sense of these signals, you just have to tap into the different signals, and you can combine together as a stream. In today's business, actually, what happens is that you have different functions in different systems. So you have your customer system, customer management system in Oracle, then you have your call logs in Hadoop, and then bringing these things together is very painful. And I tell you from experience, even at Yahoo, we had the click logs on some Hadoop cluster, the user profiles on another clusters, and putting things together is painful. And this hinders the amount of innovation you can actually bring on. So having a central place where all these signals are collected is actually a huge boost for innovation. It makes developing applications much faster. What in the end you want to obtain by creating this data nervous system is what I like to call perishable insights. So these are insights that have a great instantaneous value. Remember this example with the Bahamas query. But whose value is ephemeral, so it decreases exponentially with time. Now, if you don't act on it right away, you're paying an opportunity cost. That's how I like to think about it. Let me give you another example. Let's say you have a web app, and usually web apps are composed, so you have a web page that is composed by calling several services. These services can answer at different speed, and each of them can have some problem. So you usually want to monitor the speed at which things load in order to diagnose problems. And given that it's a distributed service, you have logs of different components that are all scattered throughout your cluster. So to understand what's going on, you have to bring all these logs together in a single place and do some analysis on them. You can do it once per day or once per hour and with a batch process. And you can do a very nice postmortem of what went wrong. But you cannot ruin time. What went wrong, went wrong. The user had a bad experience, and there's nothing you can do about that. Instead, if you continuously process these logs and you aggregate these logs, publishing metrics for this web application, you can easily build a monitoring and alerting service which alerts you as soon as something goes wrong. And this gives you the opportunity to fix it right away and give the customer a much better experience. So the last reason why you should care about stream processing is because, in my opinion, it's going to be commonplace very soon. So maybe it's a bit hard to read, but you see that here we have big data, and just a bit above we have complex event processing. This is Gartner's hype cycle from 2014. And as you know, big data now is the buzzword. You cannot turn around without hearing it. And it's just a bit farther ahead than complex event processing, which is another jargon for stream processing or stream analytics. And why I say 5 years? Well, because if you look at 2010 and you look at where big data is, where is big data? There is no big data. So in 2010, big data was off the radar. There was no big data yet. And in 5 years, we are surrounded by it everywhere. And this is because, as I said at the beginning, change is accelerating. So in just 5 years, something that was not there became so commonplace. That's why my prediction is that in at most 5 years, we will be dealing with stream processing every day. Okay, so hopefully by now you are convinced that you should care about this. How do you go about and build something that resembles a data nervous system? Now, this is the section that is a bit more technical. I hope that is going to be understandable. So the architecture of a data nervous system, as I said, resembles the nervous system. You have the peripheral nervous system, which is your sensor that gather the data from your processes. Then you have your spine, that is where you put together all the signals, and then you bring them to the analysis, to your brain. And these three components, you can assemble them in different ways. So, of course, you can go with some commercial solution, such as EVAM, that has a very well integrated platform for doing this. However, I'm most familiar with the open source projects and the Apache Software Foundation because I'm a contributor and committer there for several projects. So for the rest of the talk, I will be speaking about open source components for building this architecture. As I said, you can go for a well-integrated solutions if you don't want to care about building your own. So the first part is gathering all your data, ingestion. And here there is no ready-made solution, especially because signals come from so many different sources that it's impossible to have a single solution for everything. So it's still very messy and very ad hoc. So if you know the refrain of that in data science, 80% of your time is spent cleaning data, well, in stream processing, 80% of your time will be spent ingesting your data or writing something that ingests your data. Anyway, there are a few components that you should be aware of if you want to build your own solution. You will be dealing with scheme evolution because your data will change and your processes will change. So Avro is a row store that allows you to do scheme evolution. If you want to do analytics in a more efficient way that only take a subset of the columns that you're interested in, you can use a column store such as Parquet. And if your problem is one of the problems that many web companies have, which is just log collection, distributed log collection, such as in the example that I made before with the web application, then there is a ready-made solution for you, which is Flume. And Flume just takes these logs and transforms them into a stream of data that you can feed into the broker and then later analyze. So the second part is the brokerage. How do you put all of these sensors together? And luckily here, there is a very mature, very well-developed component, which is Kafka. So Kafka is, all of these are Apache projects. This was open sourced by LinkedIn. And it builds an abstraction of a resilient distributed stream. So you can put everything into this stream and then subscribe to this stream in order to receive new events that come and then process them. So you can use Kafka as the spine of your data nervous system, and everything will connect to it. So application will feed off it, sensor will write to it. You can write to databases, and you can still, of course, connect to batch analytics and Hadoop by just flushing the stream into a Hadoop file system, for example. So this is how the architecture looks like at the broker level. At the processing level, again, we have multiple solutions. However, here there is a bit more order and convergence. All of these are, again, Apache projects, S4 open source by Yahoo, Samza by LinkedIn, Storm by Twitter, Spark Streaming by Berkeley, Flink by TU Berlin, and all of them have the ability to process streams, and they do that by using the so-called actors model, which is depicted in the slide. And the idea here is that you have a stream, you partition it into substreams that can be processed independently on different machines, and then you produce new streams that you can shuffle around and send to the next layer, composing a pipeline or a graph of operators that will build your pipeline. And the final output of your application will be another stream, so a transformed stream. For example, you can grab all the logs together, put them in order, and extract metrics from them, just saying how much delay the user has experienced on average. And there is one more component that is not exactly part of the data nervous system, but is still very important, which is the output. So what do you do with this stream that you have created with your application? Well, you can put it back into Kafka, and this is very useful if you want to compose applications. So it's like publishing a service for the rest of your company. Or you can put it into a key value store, for example, Cassandra. And in this case, you're creating a view of the stream. And this view of the stream will enable you to create reactive applications. Let me give you an example. The current paradigm to build applications is the request response. So you have a user on a web browser that does a request. It goes through the cache or through the database. You have some business logic there. So every time there is a request, it goes through the whole stack. So if something changes, it's very difficult, especially for the first part, to update online. While in the browser, it's easy to create reactive applications with JavaScript. A different paradigm is if you do something like this, a subscribe notify. The client subscribes to a view of the stream. And these views are kept up to date by continuously ingesting events. And whenever something changes in the view, you can do a reactive callback to the user. Take, for example, Excel. You have a cell that is a function of other cells, and whenever you change one of the input cells, the formula automatically gets recomputed. It's the same idea. Okay. The last thing I want to speak about is maybe many of you have heard about Lambda and Kappa architectures. And I want to spend just a minute speaking about them because it's a huge debate in technological circles. So the Lambda architecture is the one on top. And the idea here is that you have your existing batch processing system, such as Hadoop, and then you have your stream processing system, such as Storm. And what you want to do is you implement your logic in both of them. You analyze your historical data with the batch system, and you analyze the data that is coming in with a lightweight streaming system, but you store also the data somewhere. And then periodically you recompute the batches and you throw away this speed table or the cache. And this works fine. It's a solution to get value from the data as soon as it arrives. However, if you ask me, this is duct tape. You're just putting together two things that are very different, and you have to spend energy to build two systems, maintain two systems, and operate two different systems. And they're very different. Whenever you change the business logic in one, you have to change it comparably in the other. Otherwise, you have inconsistencies. The CAP architecture is the one below, and the idea is that you can do without the batch layer completely, because the systems, the processing systems that we have nowadays are actually powerful enough to take historical data, stream it through the system, and produce a view of the application. So especially for production applications where you don't need huge exploratory analysis, you have something that is there, it's much easier to do without the batch layer. And you can even have different versions of the same application running concurrently, because they can subscribe to the same data, and you can compare the output, and you can validate that the new version does everything correctly before switching the application from one view to the other. So it's very convenient in some sense. Okay, so the next question is where? All of this is very nice, but where does it apply? What are the application domains? So I have seen several applications of these technologies in industrial application, in telecommunications, in web, of course, and especially for the Internet of Things, which is what is happening nowadays, that everything is instrumented. So there are sensors everywhere. And this is something that web companies used to do, to instrument everything on a web page, and now we are instrumenting everything in the real world. So each of you has probably several sensors that are registering data right now. In industrial applications, one of the most compelling and actually used applications is predictive maintenance. So let's say that you have a field of wind turbines, and they're producing electricity, and once in a while, one of them breaks down, and you have to send a crew to repair it. But of course, the crew is not right there, so between the moment that it fails and the crew repairs it, the turbine is down. And this is cost, because you're paying the turbine, but it's not producing any output. You could, of course, periodically send your crew to check all the turbines, but you have to put them offline while they're checking, and also you have to pay your crew more because they are working periodically, not on demand, and they will spend more time just checking, just doing busy work. What people are trying to do instead is doing predictive maintenance. You have data from turbines that have broken down, and you know the pattern, so you can start seeing that something goes wrong before it actually completely fails. So it's not a sharp shift, but it's a slow decline. And by learning how this happens and learning to recognize this from the data, you can send your crew right in the moment where the turbine is going to fail. So this brings down the costs, both from the turbine being offline and failing, and also because you can repair things before they completely burn, and also from the point of view of the time from the human beings. Another application that is especially common in the web is text search. Imagine Twitter. So in Twitter, you can have queries. For example, you can look for hashtag. And from that moment on, Twitter will analyze all the tweets that are coming in, which are several thousands per second. And whenever there is a tweet that matches your query, will give you a notification that a new tweet has arrived. And if you think about it, there are millions of queries with millions of documents, tweets arriving. So this is a very clear, challenging application domain, and where the stream processing is absolutely needed. You couldn't do it in any other way. And there are technologies for this, of course. Twitter, LinkedIn have both worked on this problem. And the idea is that you index your queries somehow and you stream your documents through. Another application, of course, is machine learning if you want to do something more fancy. And here, one of the projects that we started at Yahoo, so shameless plug, with Albert Biffet, is Samoa. Samoa is currently an Apache incubator project and does all of the things in the top row, so classification, clustering, regression, frequent pattern mining, on top of all the systems on the bottom row. So you can do streaming online, machine learning on top of a distributed systems, and this will help you with more complicated problems with predictive analytics. And finally, for problems that are in the space of the Internet of Things, where usually the data is very simple, you can think of your data as a time series. So it's a single sensor that is a single value that changes throughout time. A typical thing is doing anomaly detection. For example, here, the system is learning what Christmas is. The behavior of consumers during Christmas is very different from the rest of the year. And this is usually a problem. When you build an anomaly detection system, the 4th of July in US is always an anomaly, but actually it is not, because people know that that's going to happen. So what you do is you build a model of your time series, and you check the difference. So you measure the actual value with your model. If the difference is statistically large, then you say this is an anomaly. And you can see that these models, of course, need to be trained online, because the way the signal changes online, but is good enough to be able to model even Christmas decently. So the recent advances make these models very good. Okay, so the last question is when you should start caring about it. What are the risks here? And this is a big issue. I think that, as I said, 5 years will be the upper limit on when you should start caring about this. But actually, there are adoption risks even for technologies such as Hadoop. So in a recent survey, Gartner has found that more than 50% of the surveyed people didn't have any plan to adopt Hadoop, which is the core of the big data technology. So even big data, which is so common, still is not as commonly adopted as you might think. And these might be just companies that are not very early adopters or very late adopters, or it might be that it's not as commonplace as we expect. And while Hadoop is very mature and is very well developed, stream processing is still just starting. So if you want to be an early adopter, there are some risks that you need to consider. Cost is not one of these risks, because actually hardware is pretty cheap, and you can always use cloud-based solutions for your stream processing. There are offerings from both Amazon and Microsoft. And if you don't want to spend money on commercial solutions, you can go open source. However, if you go this route, you will find several issues. So first, it's just inherently harder to do stream analytics, because it's like patch analytics plus an additional constraint that you have to analyze these things fast, and you don't know what's coming at you. Second, as I said, it's a new thing, so all the operations, the best practices haven't been ironed out yet. While there is a huge knowledge in companies such as Yahoo, Google, Facebook on how to deal with the big data problem, with streaming, even these companies are just starting out. Of course, this translates in a huge lack of skill, training, and support, especially in the market. That's why you might consider commercial solutions, because that will give you the support you need. And finally, you need to rethink your applications from scratch in any case, because you need to re-implement them. So this is a cost that you need to pay for getting the value out of your data, out of the freshness of your data. And finally, you should consider whether this thing is worth it, whether you can actually derive any actionable insights. So you have your perishable insights, but can you really act upon them? If the answer is no, then maybe it's not worth it. So you need to be careful in defining what you want. And given that things change very fast, this thing will be a moving target. So you have to engineer and architect your solution in such a way that is very easy to change continuously. And finally, one more point is that if you, so any analytics is just a function of your data. If you put garbage in, you will get garbage out. So most of the time in building a data stream architecture, you will spend it cleaning your data because you will realize how many data quality issues you had and that you had not realized before. So again, 80% of the data science is cleaning data. So concluding, I answered 5 of these questions. I left one out, so, which is who. So the 5 questions I answered were what is stream analytics, and why you should care about it to obtain perishable insights, and how you go about building an asynchronous processing architecture for streaming data. I showed you that this applies about everywhere, so there is a very large number of application domain. And I told you that in at most 5 years, this thing will be commonplace. That's my prediction, at least. But the last question is, who will benefit from it? Who will be the big players in this setting? Who will be the fast fish? Thank you.